When it comes to numbers and measurements made in any scientific field, the numbers can sometimes be so big or so small that it doesn't make sense to write them as incredibly long whole numbers or decimals with a whole heap of zeros. So a good way to represent these numbers in a compact, concise way is to use scientific notation. Both the extremely large and the extremely small numbers can easily be represented using scientific notation. Let's see how using scientific notation may help us understand exactly how far away the furthest known galaxy is located. The galaxy MACS 0647JD is located at a distance of 13.39 gigalight-years away. That's 13.39 billion light-years. Keep in mind, a light-year is not a unit of time, despite that it sounds like one, but rather it is a unit of distance. 1 light-year is the distance that light can travel, and at the fastest known speed possible too, in the span of 1 whole year, which turns out to be about 6 trillion miles. That means that this galaxy is about 78 billion trillion miles away. To get a sense of exactly how big this number actually is, think of it in seconds. There are 60 seconds in 1 minute, so 100 seconds makes a little over a minute and a half. 1,000 seconds is almost 17 minutes, and 100,000 seconds is a little over a day. 1 million seconds is about the same length of time as 12 days, but 1 billion seconds jumps to 32 years. So you can only imagine exactly how gargantuan a number like 78 billion trillion really is. And this is why we like scientific notation. Now, if we have numbers like the ones we've just seen, how can we rewrite them in a more concise way? Well, we would have to use scientific notation for that. To write a number in scientific notation, we write a number between 1 and 9.99999 and multiply that number by a factor of 10, like 10, 100, 1000, or even tenths, hundredths, thousandths, etc. For example, the number 41,000 can be written in scientific notation as 4.1 times 10 to the power of 4. Similarly, the number 278 billion can be written in scientific notation as 2.78 times 10 to the power of 11. Notice how both of these numbers were whole numbers originally, and that they both have positive exponents? Well, what happens now if we have a decimal value that's really small? A partial decimal, less than 1 in its value. Here we have 0.0006245, which can be rewritten in scientific notation as 6.245 times 10 to the power of negative 4. Anytime we see a negative exponent in scientific notation, that implies that the number originally is very small, less than the number 1 in its size. Let's take a look at a couple examples where we'll figure out exactly how to write numbers in proper scientific notation. So in the first example, we have the number 35. Now 35, written exactly as it is not represented in proper scientific notation. Not yet. So what we would have to do is first identify where that imaginary decimal point is located, behind the last digit in the number. Then you would move this decimal point as many times as is necessary until it finally sits behind the first non-zero digit of the number, in this case, the 3. Having done this, we can now write 35 as 3.5, but we have to multiply 3.5 by some factor of 10, meaning there's got to be some exponent on top of the 10, to still represent 35. So how do we determine what that exponent will be? We have to look at two things. We look at the direction that we moved the arrow, and we also look at how many times. These two parameters will help determine what the exponent should be on top of that base 10. So in this case, in the first example, we only move the decimal over once and to the left. So that means the exponent will be a positive 1. In the second example, we have the number 67,429. In order for us to write this in proper scientific notation, we again have to identify that imaginary decimal that sits behind the last digit. And again, we move it over as many times as is necessary until it sits behind the first non-zero digit, in this case, the 6. Having done that, We can now write this as 6.7429, but we still have to multiply by a factor of 10. To determine what that exponent on the 10 will be, look at how many times you've moved that imaginary decimal and in what direction. According to this little diagram we drew here, we've moved the decimal over 4 times. Is it a positive 4 or a negative 4? That depends on the direction you moved. Have you moved to the left? In this case, we have. That makes it a positive. So we have a positive 4 on that exponent. In the next example, we'll see what brings forward a negative exponent. We'll start with a tiny number, 0.00213. Here, the main difference with this example and the previous two is that the decimal point is not imaginary, it's actually part of the number. In fact, it's located right here. So you don't have to determine where it is, you just have to move it. And again, you move it until you finally place it behind the first non-zero digit in the number. In this case, we move to the right and we place that decimal behind the 2. Having done that, we can go ahead and write this number as 2.13, but we still have to multiply it by a factor of 10. So in this case, the exponent on top of the 10 will be a negative number because we've now moved to the right. How many times you move over to the right determines the value of your exponent. So in this case, we have 10 to the power of negative 3.